Hello, my wonderful AP Chemers. We are going to talk about covalent bonding today and molecules that contain covalent bonds. So, in molecules or covalently bonded substances, the electrons are shared as opposed to given and taken in ionic, so that they achieve the lowest energy again. So, any type of bonding happens so that you form a substance with lower potential energy that is more stable and lower in energy. So similar to the diagram or the graph that we saw for NaCl, which was ionic earlier in the notes, here is a diagram for H2, which is molecular. But it is kind of the same idea. So if you remember, the y-axis was the potential energy in kilojoules per mole, and we know that the lower the energy, the more stable something is, the more favorable it is to exist, right? On the x-axis is the internuclear distance again in picometers, which is the distance between the nuclei. So the distance between this hydrogen nucleus and this other hydrogen nucleus. So essentially that internuclear distance is basically the bond length. So again, there are repulsive and attractive forces. So the two nuclei are attracted the two nuclei are attracted to each other just because of their masses. Any two objects that have mass attract each other. At the same time, your electron clouds are going to repel each other. And so here they are too close, so there's too many repulsive forces. Here they're too far apart, so there's too many attractive forces. And so here, this would be the perfect balance between the two. And we know that this is the perfect balance because this is the lowest energy possible. So we know that in reality H2 will exist like this because that is the lowest potential energy, so it is most stable when it's that way, so it's going to remain that way. And based on this, when we read the lowest energy, we go up to the x-axis, and this, whatever R naught is or RO is, that is going to be our real internuclear distance, which is the real bond length. So you just need to be able to read what this graph is saying here. Let's think of some properties for covalent substances. So covalent substances have much lower boiling points and melting points than ionic substances are. They do not conduct electricity, whether dissolved or solid or liquid or whatever. They most are insoluble. Although not all, of course, in water. Okay, now whether it's ionic or covalent, it's not as clear-cut as we think. So last year we talked about that ionic substances are when you have a metal bonded with a non-metal, versus covalent is when you have two or more nonmetals bonded together. Now that's not really exactly true. It is true for the most part, but it's a generalization. It is more of a continuum where ionic is one extreme and then nonpolar covalent is the other extreme. So this has to do with electronegativity. So electronegativity is a measure of the ability of an atom to attract electrons to itself in a bond. And so electronegativity doesn't have units, but we do know that it increases as you go across the periodic table and decreases as you go down the periodic table. Noble gases don't really have values because they don't really form very many bonds. So fluorine is the most electronegative atom on the periodic table. Francium would be the least electronegative, excluding the noble gases. So if I take two hydrogen atoms and bond them together, they are sharing those electrons. And they are going to share those electrons equally because they have the same electronegativity. Both of the hydrogen atoms have the same electronegativity. And so they are going to equally share these electrons. Their ability to attract the electrons to themselves is the same. So they're going to share them exactly equally. Now let's look at HI. So if I look at HI, this bond is slightly polar or moderately polar. That's because there is a little bit of a difference in electronegativity between hydrogen and iodine right here. Right? But that difference is not very big. There's some, but it's not very big. And so it puts a slight negative charge on the iodine. It puts a slight positive charge on the hydrogen, but very, very little because their electronegativities are similar. And so we say little unequal sharing. I'll say slightly unequal sharing of the electrons. And now let's look at HCl. So hydrogen is still here, 2.1. Here's chlorine, 3.0. The difference between hydrogen and chlorine's electronegativity is a little bit bigger. And so the chlorine is going to be able to pull the electrons towards it a lot more than the hydrogen will. And so this is definitely unequal sharing of electrons. Okay, now let's look at HF. So hydrogen is 2.1, fluorine is 4.0. Ooh, that's a huge difference, right? So fluorine attracts electrons a lot more than hydrogen does to itself. And so this is very unequal sharing. Now if we were to, here's HCl and here's HI. If we were to show the partial charges here, the chlorine would have a partial negative and the hydrogen will have a partial positive, but because of the difference in electronegativity being more here than there, this is going to be a bigger partial negative and this is going to be a bigger partial positive. And this one, oh, I'm sorry, that's an S. This one, the electronegativity difference is huge, so that's going to be a huge partial positive. It's still not a full positive and a full negative, but a much larger partial positive and negative than the other two. Now let's look at KF. So K is right here, it's 0.8, and fluorine is 4.0. That's an even larger difference. The difference here is so great that it's extremely, extremely, extremely unequal sharing, that it is pretty much not sharing anymore. It is giving and taking. So we're losing and gaining electrons here. It is a full positive on the potassium and a full negative on the fluorine. These are real charges, not partial charges, because fluorine is attracting the electrons to itself way more than the potassium. So the electrons are basically not spending any time with the potassium. They are just with the fluorine. And so you can look at these, partial positives and negatives and full positives and negatives. You go from full positive and negative in ionic to a pretty large partial negative and positive, a little bit less partial positive and negative, kind of tiny partial positive and negative, and no charges whatsoever, no partial charges even whatsoever here in nonpolar. So it is a continuum. It's not a clear cut. It's hard to say where exactly the electronegativity difference should be in order for it to be ionic versus, covalent. That's really polar. So what attracts these particles together? Well, that positive and negative attraction, whether it be a full positive and negative or a partial positive and negative. But obviously, a full positive and negative is going to have much stronger attractions than something that is partial charge. And so when it comes to the attractions, the Coulombic attractions, extremely strong and ionic. I'll say very strong. We'll say here strong. Maybe weak. We'll say weakest. Okay. You don't have to know, you don't have to call it strong or weakest or whatever, but the idea is the continuum. Maybe even instead of all this, maybe you can just say, so I'm gonna maybe go like this and say weakest, and I'll go here strongest. Maybe do that instead of labeling it. But again, it is a continuum in terms of Coulombic attractions, in terms of the sharing, and in terms of the positives and negatives, or partial positives and negatives. Now, let's look at, we were talking about the actual bonds here, the intramolecular force, right? The force of attraction that holds these things together, the actual bond, right? Now, let's talk about intermolecular forces. So, if I were to take an HCl and another HCl, what type of intermolecular force is there? Or so if you have an H2 and another H2 here, that force of attraction, that's the intermolecular force. These are London dispersion. Do you remember that? Which are the weakest type of attractions. This one, if I have an HI and another HI, and I look at the attractions between them, those are called dipole interactions, or dipole forces, either way. And they're much stronger than London dispersion. Now let's look at HCl. Still dipole interactions, but these are stronger dipole interactions because the partial positive and the partial negative are larger than this one. So this would be stronger dipole interactions than that one. Let's look at this one. So if I have an HI and another, an HF and another HF neighboring, the attraction between them, what would we call that? H bonds, which are stronger than dipole. How about, oops. I didn't mean to make it that way, but it doesn't really matter. Okay, plus, there we go. How about the attractions here? Full positive and negative attraction. So we call these ionic interactions. And these are way stronger. So in terms of intermolecular forces, these are the strongest. And these are, I guess I already wrote weakest. So why is that? Because of the Coulombic attractions being strongest here and weakest there. So again, the purpose of this is to see that it is a continuum where one extreme is ionic and then the other extreme is the nonpolar covalent. Okay, let's look back at this electronegativity table here. And you'll see in different textbooks, they have these ranges of what we would consider nonpolar versus polar versus ionic. You do not need to memorize these numbers. In fact, these numbers are different in different textbooks. They're close, but they're different. So they kind of come up with a number, but I don't know if I would trust that cutoff. You do not have to calculate these. You do not have to memorize these numbers or anything. This is just to show you how we classify them. So if it's a big difference in electronegativity, we call that ionic. If it's a very small difference, we call it nonpolar. And if there's a reasonable difference, then we call it polar. The dipole moment indicates direction of the bond polarity, and you can do a dipole moment for the bond itself or for a whole molecule, and we'll see that a little bit later when we draw covalent substances. But we say that a polar substance has a dipole moment, and we show an arrow to where the direction of the electrons are going. Let's try to answer these. It says, which is the more polar bond in each set? So CSF or LII. So what you do is you look at the differences. I guess I shouldn't have written all over this. If you've been watching the videos of the notes, you know I struggle with the eraser for some reason. Okay, I'm gonna try to mark them with lighter colors this time so we can still see. So let's go with that color. So CSF or LII. So CSF, so there's fluorine. CS would be like right here. So there's that one versus the other one is LII. So there's lithium and there's iodide. You can tell definitely that the difference between the CSF is much larger. You're going from the corner of the periodic table that's the lowest to the corner of the periodic table that's the highest. These are not the lowest or the highest, right? So they're pretty similar. So this one is definitely more polar. Okay, now CSS, so CS is down here and sulfur's right there, versus PP. Well, you don't even need to look at anything. This is the same atom, right? So they're going to have the same electronegativity no matter what. And these are going to have different electronegativity. Whether that difference is big or small, it doesn't matter. There's a difference, whereas this one, they're equal. So this one's definitely the one that's more polar. Okay, next one is carbon, along with, so there's our carbon, oxygen or sulfur. So this one or this one. Based on where they are in the periodic table, you can tell that the carbon and the oxygen, that one is more polar, a more polar bond. Okay, now that's for an individual bond. How about if your molecule itself is polar or nonpolar? How do you do that? Well, you look to check if you have at least one polar bond and if your molecule is symmetric or not. So for a molecule to be polar, you've got to have a polar bond and it has to be asymmetric. Not sure if I spelled this right. So let's start with carbon dioxide. So carbon dioxide, I'm just going to add the lone pairs here. All right, so the key to doing this is that you draw it with the correct geometry. And then you draw the little arrows that point to where the electrons are going in each bond. So carbon and oxygen. Oxygen is more electronegative, so in this bond the electrons are going this way. In this bond the electrons are going this way. The question is, are they canceling each other out or are they adding up to a direction? So the answer here is, if you drew it correctly with it being linear, they cancel each other out. And that tells you if they cancel, it's symmetric, it's non-polar. So this one is non-polar. Another way to tell is if you look at the center of your molecule and you look around it, if everything around it is the same, then that means it's symmetric and it's non-polar as well. Let's look at water. So here are my lone pairs. And what I do to find out if it's polar or not is I draw my little arrows. So oxygen, hydrogen, oxygen is more electronegative, so the electrons are going towards the oxygen here and going towards the oxygen here. And you see that they don't cancel each other out. They add up to this direction right here, right? And so the electrons are being pulled towards the oxygen portion of the molecule first, more, so this gets a partial negative, and then these get partial positives here. So that means that this is definitely a polar molecule. And if it's a polar molecule, you need to be able to draw the dipole moment, and so the dipole moment is this big arrow right here. Now it's important to know how to draw this summation arrow. You also might want to either draw the little arrows for each of the bonds very, very light or very, very small, or erase them, because there should not be any confusion as to which one is the arrow that you're drawing for the dipole moment. Now, what if you had drawn water? Oops. What if you had drawn water like this? Then if you drew your arrows, you'd see one going this way, one going this way. It looks like they cancel each other out, don't they? And so in order for you to be able to use these vectors, these little arrows correctly, you have to draw it with the correct geometry. And so to help you not get it wrong because of that, another way to tell whether it's polar or not is you look at the center of the molecule and you look to see if everything around it is the same. So we see lone pairs, we see single bond hydrogens, these are different things, and so that means it's not symmetric and it is polar. Okay, let's go to the next one. Just draw my lone pairs here. Lots of lone pairs. Okay. I'm going to do it a little bit darker. Between these two, chlorine is more electronegative than carbon, so you have an arrow this way, an arrow this way, an arrow this way, and an arrow that way. Do they cancel each other out? Yes, they do. If you draw it either this way, or actually the more correct way is tetrahedral. If you imagine a tetrahedral in your head with all of them pulling with the same strength, then it is symmetric. They cancel each other out, and this one is non-polar. Okay, let's look at the next one. Let's put our lone pairs. Okay, so if we draw our arrows here, this one goes that way, this one goes that way, this one goes that way. And I'm not actually sure carbon or hydrogen is more electronegative. 2.1 versus 2.5. So carbon's slightly more electronegative. So it actually goes this way. And so that would definitely be polar. Even if hydrogen was slightly more electronegative than chlorine and the arrow is going up, it still they would still not cancel each other out. And so my net would be going this way. This one is polar. Okay, again, make sure that you can tell which arrow is your net dipole moment. You can also, if you feel like it's going to hide your diagram and you're asked for the diagram, you can draw it on this side. You can draw it like that. Okay, NH3. So let's see, nitrogen is more electronegative. So you have your three arrows pointing towards nitrogen. They do not cancel each other out. The net is going towards the nitrogen. Again, you can draw it in there. I'm going to draw it right here, but you can draw it on the side if you'd like, and this one is polar. Okay, BF3, let's put our lone pairs. It's kind of hard to draw lone pairs with this. There we go. Fluorine is more electronegative than boron. So I have an arrow this way, an arrow this way, an arrow this way. They are 120 apart, and they are pulling from opposite directions, and so this one is non-polar. Again, you can use the in the middle of my molecule, everything looks the same, whereas this one, it does not look the same because there's a lone pair here versus hydrogen. So this one's polar, but this one's non-polar. If you look at this one, hydrogen versus chlorine, they're different, so that one's polar. So that also checks out. Both ways work most of the time. Okay, let's go to the next set. So this one, we have one fluorine and then 3 chlorines bonded to that carbon. And if you draw your arrows, chlorine is more electronegative. Fluorine is also more electronegative. It looks like they cancel out, don't they? Problem is, yes, they are pulling from opposite directions, but this one is pulling more than the other 3. And so that one is actually polar, even though it looks like the little arrows are canceling out because the magnitude of this arrow is bigger than the other arrows. So this is where, it helps if you look around your central atom or the center of the molecule. There's fluorines, there's chlorines, they're different, so that is polar. And the direction of the dipole is towards the fluorine. Okay, last one here. Let's draw our lone pairs. So chlorine is more electronegative than carbon. I'm going to go ahead and change these to fluorines instead of hydrogens. There we go. Okay. Fluorine is also more electronegative than carbon, right? Do they cancel each other out? The answer is yes, they do. And this is polar. Why is that? Because in reality, you have your carbon, right? And then you have these 4, and in reality, like if you imagine a tetrahedral, so let me actually draw this in a different way. So let's say this is your carbon. One of them is here, one of them is here, and then one of them, this means it's going towards you, and one of them is going away from you. Dashed lines in chemistry, when you draw structures like this, these are in the plane of the paper. This one's going back and this one's going to the front. No matter how you look at it, wherever you put the fluorine and the chlorines and all that, they're not going to be canceling each other out. If you put, let's say, the fluorines here and the chlorines there, well, one is in the plane and in the back versus plane and front. They do not cancel each other out. Those 2 are going to pull more towards them than these 2 would. It's kind of hard to visualize that without a picture, but in this example, the way that I have it drawn, the arrow would be looking towards you. It's really hard to show it here because we're drawing 3D molecules on 2D paper. So the only way that you can really show it is if you draw it so that it's like this. And if you think about it, those 2 are the same molecule. You're just looking at it from a different angle. So if you were to draw it like that, then the dipole moment would be shown this way. It's impossible to show it like this. but this is definitely polar.